industry. And we always not look for definitely the profit, but next to profit, we also look for the health, environment, and all other things, the carbon footprint we would like to decrease and everything. Okay, so let's go to the technical part. You all know about MOSFET. So it's a 3-terminal device, source, drain, gate. So it is a in channel. So it's a P well, and we dope this side N plus, N plus. And then we have a channel, we have a gate oxide, and we put a gate voltage, positive gate voltage. And then there's inversion of channel, and then we put source and drain voltage, and the current is flowing from here through the channel. Because of the positive, the electron will be attracted, hole will be repulsed, so there will be a channel formation. Now, we need to scale this. So we need to make it small. So what we should do? On the same time, we have to improve the performance. So we can reduce the thickness of the gate oxide, but that has a diverse problem. If we go like really below thickness, then there will be a gate leakage. So the gate, whatever we apply, it will come to the channel. There will be a leakage. So we cannot really go down for the TX. So solution would be we can use a high-K material like hafnium oxide, which is very popular, but still, on the other hand, when you shrink from this side, you have to shrink from that side also. So if you shrink from this side, the channel length will reduce. So what will happen? Your short channel effect will come in picture. Like both this depletion region will kind of join, and it would be a leaky. So even if you are not applying any voltage, your transistor will be on. And so your gate cannot control the device. So that is a big problem with the scaling down of the planar MOSFET devices. How can you reduce that? We can have a shallow junction like this. We can reduce it by a shallow junction. But again, if we have a shallow junction, then there will be a parasitic capacitance between this and this. So again, the performance would be decreased. So what we can do, we can have two different kind of doping. Like we can dope this area lightly, which is very near to the gate, under the gate. And the other side, we can dope it high. So in that way, it's kind of hollow thing. So we can reduce the short channel effect. But still, it's kind of, when we're scaling down, we are kind of coming to the atomic level. So now it's kind of consuming more power since it's kind of leaky things. So there will be a lot of other effects. You can, these are pretty simple things, and you can search the theory part. I'm not going in detail. So that's the summary of MOSFET. If we scale down, what would be that thing? The leakage is the main thing, and the short channel effect would be the main, and other things. So that's the thing. The gate has no control over channel, and then the power is draining. So you are consuming a lot of power, but you are not using it. So what's the solution? So around 2011, really industry come up with the FinFET device and trying to go from the MOSFET to the tri-gate. It's called tri-gate. Intel is called tri-gate. Somebody is called FinFET. So it's simple, like, so this is the planar transistor. Just move it. You just flip it the other way. So that's called the FinFET. And you have like the channel is elevated. I'm getting some background noise actually from someone. So the channel is like elevated, stick up on the air, and that's called the fin. So this is called the fin. and this is called the fin. And then the gate is all over that side. So on the three sides, gate is like surrounded. So that way your gate control over channel is way higher, way better than any MOSFET device. So you can control from both sides. And another thing is that you can shrink the size. You can reduce the size of the channel, and you don't need to make a doping things. So your leakage current will reduce, your power consumption will reduce, and you can really scale up. That's another thing I will come up. You can just increase the number of fin to go to a very power consumption device and an efficient device. So that's the Intel design, probably in 2011 TriGate. So if you compare to get some idea, compare MOSFET and FinFET, it's like the gate control is less, here is more, and the construction, you can have a multi-gate in case of FinFET, but really in MOSFET, you cannot do any multi-gate. It's very difficult, and still it's taking a lot of space, a lot of area on the wafer. So you can go up vertically, but you are not allowed to go horizontally. So because the cost per chip area is more if you go this way vertically, horizontally. But if you go that way, that's okay. So anyway, so MOSFET cannot go that way, and that's the problem with the multi-gate. And its speed is slow, its leakage current is high, and channel doping is another problem because you have to dope different area with the different doping concentration. That would create a lot of mess with ion implantation. You have to do like multiple time litho and do the ion implantation. So the scalability, in one word, scalability is not favorable to MOSFET, whereas scalability is highly favorable for FinFET. So how we build the FinFET actually? So think about this as silicon thing, and this is silicon fin, and the gate is on. And you can increase the number of fin, and with the performance of the device, the current will increase, the performance of the device will increase. But how do we make this? So that's what I would like to present here, so that you can get some idea that what is the steps process in the fabrication process, how we can build it. One more thing I would like to add. So here, the source and drain. So as I said, in the MOSFET, that you have to dope differently, because to reduce the parasitic capacitance between the source drain and the gate. So here, what we do, we are doing the epitaxial source drain metal. So when you do epitaxy, then, and we have to anneal. So the fin channel of the FinFET is not doped. But when you do epitaxy and you go to high temperature for anneal, there will be the carrier concentration will go a little bit inside. So that way, it will automatically create that low doping region near to the gate and highly doped area here. Will form silicide, it's called silicide, where the metal and the silicon will mix and make an alloy, which is both way electron can go, is silicide, where the doping concentration will reduce as we are going inside the channel area. So that way you will get a nice gradient. And if you take a TEM, cross-sectional TEM, it will look like this. Why I'm saying, because you will see the process. So let's go to the process. So first we will take a silicon wafer, right? And then we will put a nitride. I'm saying dielectric. I'm not saying any particular material, say dielectric 1. And then on top of that, there will be a dielectric too. It can be nitride, it can be oxide, based on what is the etch selectivity. And then we will pattern. So we will pattern for like number of fins, okay? And then we will etch silicon first. So you can say why you are not directly etching on silicon.
One second.
Sorry.
Regarding that Kitle 2470. Yes.
Mute him. I muted him. You can ask her to continue.
Sir, please continue.
There was some disturbance there. Yeah.
Okay. Can you please mute everyone? Like, yeah. Okay. So on silicon, we are doing the fin first, and then we are etching the silicon, right? We are etching up to some extent. And we are giving this dielectric 1, dielectric 2, because we need a specific angle. It cannot be like this. It has to be like 90 degree, maybe a little bit. It will never be 90 degree angle anyway. So let's move on. Then we will fill with oxide and CMP. CMP is the chemical mechanical polishing. So we'll fill it, we'll like smoothen the substrate wafer. So we fill it with oxide. And then what we'll do, we will etch the oxide, wet etching. It's called wet etching. And then we can do some dry etching also, like wet etching a little bit, only oxide. So the oxide and the silicon has etch selectivity. We'll only etch the oxide, not the silicon, so that we can get the fin. See, you see the point here, how we were getting from the bulk substrate to the fin. So we're first etching the silicon and then filling with oxide, and then a little bit recessing the oxide, and then we get the fin, right? And then we are putting a dummy gate. It's all a dummy gate. It's like a material, we are just filling it up. We will remove it later. We'll see it. And that also like filling it, CMP. There are a lot of steps I'm skipping, but that's the major steps. So next we will come with another mask. Mask means reticles, where how we want to arrange the device. So the reticles, and then come, and then we etch the dummy gate. And that dummy gate, so it is kind of gate, the dummy gate, why I'm saying, because we will remove it later and we will put the actual gate at the last. So that's why we call it dummy gate. And so the little part is extended on the other side, and where we will put the source stand thing. And then there are low K spacer. So you need a spacer, I said, otherwise the parasitic capacitance will be high. So we need a spacer, and then etch the spacer directionally. So there is, isotropic etching and isotropic etching. You can go through your books, like we can etch unidirectionally, we can etch directionally. So it is kind of a directional etch from the top. So we expose this area and then we chop it totally. And then so that it will go a little bit inside, and then we can do the epitaxy, so that the epitaxy would be outside, and then when we will anneal it, and anyway, the epitaxy is at high temperature. So the carrier will be diffusing inside the fin and go close to the gate. And that way we can have like less parasitic capacitance. On the same time, it will connect to the channel. So that's the purpose. And that way, that's the best part of the FinFET. And also we are using in another advanced node. And then we are removing that dummy poly. So that's a polysilicon here. We are removing the dummy, cannot really see in a bigger picture. And then we are putting high K material, that's the yellow, and then the red is the metal, filling metal, and then CMP. So now we get like the source. This is the source, and the inside is the drain, and that's the gate. And the gate oxide is high K. And then we do some contact etching from the top. So that's the overall flow, how we make the FinFET. So if you go to the industry thing, so really FinFET, I don't want to spend much time, but like when we are going to the industry node, like 20 nanometer, 16 nanometer, 28 nanometer, 20 nanometer, 16 nanometer, and then 10 nanometer, 7 nanometer, 5 nanometer. So that's all like a FinFET, first generation, second generation. We are increasing the number of fin here, and we are making it too tight. And then this red is the P-type, and green is the N-type. So P-type, N-type is like a CMOS kind of thing. And then we are increasing it, decreasing it based on how much current do we need. So that's the goal industry is moving. But when you go to like 7 nanometer, 5 nanometer, it would be too difficult for the fabrication process. So we need to think about something else. So here comes the ALD, the use of ALD. It actually revolutionized the industry. That's our Tokyo Electron ALD tool, and that's our fab. And I'm holding the 200 millimeter wafer here. So what is conformal deposition? So when you do different structure, you cannot deposit in all surface unless there is a ALD. With the CVD or any other deposition, it's kind of depositing from the top. So you cannot deposit inside or any difficult structure. So that's the problem, that we cannot design any kind of device because we cannot deposit on any surface. We have just deposited from the top. And that's why this conformal deposition come, and where ALD could be very useful. Like ALD is like a chemical deposition. So one precursor is the chemical. So like we want to do like silicon dioxide. So there are two precursor. One precursor is gas for silicon, and another gas is for oxygen. So silicon is coming with the gas. So it's called LTO, and it's coming and doing some reaction, and then silicon is depositing, and then we are pushing nitrogen to clean up the surface, and then we are giving oxygen, and then SiO2 is forming because the silicon has some dangling bond on the top. So that way ALD work. So that's the beauty is one monolayer, but one cycle. So this cycle, we are going like 100 cycle, 300 cycle, like that. So in that way, we can deposit on any surface. That's the beauty of ALD. And that's our fab, Tokyo Electron ALD system. You see how big it is. This is 200 millimeter. It's only 8-inch wafer, and it can hold 110 wafer. So at one shot, we can deposit on 110 wafer of each 8-inch, 200 millimeter substrate. We have same for 300 millimeter, which is 12-inch, and that is, I believe, is 150 wafers. So at the same time, we can do 150 wafers. So that's the size of the industry. I would like to give you some idea. And yeah, as I was talking. So this is the other Tokyo Electron ALD tool. So this is like single wafer tool that's specifically for high K dielectrics, ferroelectric materials. And this is like 300 millimeter tool, which is a batch tool, which is kind of 150 wafers it can take. And that's a semi batch tool, another tool. So all this focused on like a mass production of DRAM and 3D NAND, all these circuits. I'm not going in detail. That's the sub fab, and where we usually keep the pump and everything, like gas and all other things. And on the top is like a clean room. So it's a class 100 clean room where everything we put the machine and we do all the deposition, litho, and all the things. And underneath the sub fab is like all the machines things are there. Anyway, just trying to give you a glimpse. So what LD2? So LD's main is the conformal deposition, and that's the main advantage, yes. And that's why we can go to gate all around, which is another device, fantastic device for scaling. So when we are going miniaturization, scaling down, so the gate all around is kind of ultimate, and it opens up everything. And not only that, ALD is a slow process, but a uniform. So that's the main thing. You need a very uniform, nice layer. I don't matter. It doesn't matter. It's slow or faster, but it's uniform. Another thing is the selective. So really, you can do some selective deposition. That's a whole new research. Like based on the precursor, you can deposit on one surface, not deposit on another surface, while both are exposed. Both are exposed to ALD, but on one surface you are depositing, and another surface you are not depositing. So that's called selective area deposition, and also like selective area etching. So this is becoming one of the interesting field, and it's a whole new research. And in the ALD conference, in a separate conference is started for particularly selective area deposition. So you can imagine how interesting is the topic. Anyway, so moving to the nanosheet, which is the gate all around. So from FinFET, we are going to the nanosheet. FinFET has been started from 2011. Now still it is going on, still it is the mainstream in the industry, but industry is moving to the nanosheet. By 2025, the nanosheet would be in production. That's the IBM said. So the point is here in the nanosheet, in the FinFET, you are like doing the litho. How you do the litho, I showed you, but there are many other steps. How you are shrinking is SADP, SAQP. If you can just Google it and read it, those things, they'll be there. But the beauty of this one is like you just doing the epitaxial growth, the epi growth of silicon. So that is defining the thickness of the fin. Now the fin is now again vertical, in planar, like a planar, but it's not on the silicon substrate rather than it is on the top, and the gate is all around. So this thickness you can define by the epi. So you can really go down to the really thickness, and you don't need to spend money on lithography, like patterning and all these things. So let's see how we can make it. I did a quick simulation for you guys. So this is like we are epitaxially going silicon, germanium, silicon, germanium, silicon, germanium. So it's a layer, like each layer, say 20 nanometer each layer. Okay, and this one is the silicon, and the other color is the silicon germanium. Now what we do again, we are patterning with a pattern with the masked radicals. So we are etching everything. Since everything is the etchant would be wet etching, and since everything is like silicon related things, so it will etch silicon and silicon germanium. So you can see it's etching the substrate a little bit also, but that's fine. Now what we do, we need to separate those things. We need to separate all this because each one would be a separate gate all around. So we want to like separate those things. So we are filling it with a liner and then filling it with oxide and then etch back to the substrate. So that's how we are doing it. Next, we are filling the dummy oxide, as I said before on the FinFET. So dummy oxide is like we are just protecting the gate because we want to do the gate later. So it's kind of a dummy oxide. You're just filling the oxide, CMP, and then we are coming up with another mask, and we are etching from the side way. And then you see, so this area is protected. This area is open because we are etching on this side only. Okay. Now we are protecting the side layers, and we are etching these sides again. So to reduce the parasitic capacitance, we cannot elongate it. We have to chop it because we need to do the epitaxial sword stain later. So this is kind of recessing a little bit silicon germanium for that purpose, like the gate and the source stain cannot be overlapped. So it has to be, should be some little bit gap. And that's where this spacer is coming. So we are just recessing a little bit silicon germanium and put some dielectric here. That's called the spacer. I mean, this is very, very important step. And without spacer, the device will not work. And then we are removing, we are doing the metal, source and metal. And then we are removing those dummy gate, as I said before. So now we can see the silicon germanium. So now we can access the silicon germanium. We etched it, and I put gate oxide, high K dielectric, hafnium oxide. And then we are putting metal and then CMP. So that way we are finishing the gate around. How it looks like, so it's video. I made a video of that. Let's start the video. How I can start the video. Can I, come on. Oh, start the video. Anyway, yeah, so the video is starting now. So you see the how I build the layer. So there is every step is there. How I fabricated the whole structure. So that's how it moves in fab in every layer. This is very specific, and each step is there. Yep. So that's the gate all around device, how you will build it. That's a very simple one. And this is the IBM in 2017. They published the first paper with a 3-fin gate all around device. So if you see from the other side, you see in my design, it's like this is the channel, this is the nanosheet, and the gate oxide is all around, and the gate metal is all around. And here is the source. On the other side, you cannot see it. Other side is the drain. So the current you will flow from here to here, and the gate you are controlling, and all three are shorted. So you are getting a huge current from each is contributing. So all three is a single device. It's one single device. You want to chop the gate actually in isolate. I mean, we have a lot of things other, but so the gate can control all these things and it's all around. So it has a really high control over the channel. That's the main purpose of gate all around. So this is the IBM nanosheet they presented. This is the cross-sectional TM. It shows pretty nice picture from one side, from the other side, how they look like. And you see from this side is like, and this white one is the high K, and that other one is the gate metal. So this is the silicon. So to separate so that there will be no crosstalk between the nanosheets, and they're filled up with the dielectric. It's a nice picture. I can start, you can see some videos actually. This video I found is pretty cool. Yep. So you get the basic idea from Samsung what they are showing. Let's see what Intel is saying. So it's a nice video that it shows that how the footprint, the total overall area of the one transistor can be shrink really shrink. So where the FinFET is still taking a large space, where the gate around will take a very small space. And the beauty is that you can like vertically, you can make one transistor on top of another transistor. You just vertically stack it. So your total cost per wafer square, in the square unit would be pretty less. That's the beauty. And you have a lot less power. So this is really exciting device structure, and that's open up everything. You can have a different device structure, and it's just coming up very rapidly. Sorry. So that's the summary that how from the planner we are going to the tri-gate, and then we are going to the gate all around, and the gate all around is way better control over the channel. And you can, you can go to the like nanometer, like 1 nanometer, 2 nanometer. Intel is planning like in angstrom level. So, and then further, you can do like whatever I was saying, that PMOS, NMOS, not the side by side, but rather you can do like a stack, so like a CFET. So that's our Tokyo Electron. We also do all the research on this device processing, so that we can improve the tool and we can support these tech giants. All these tech giants is doing research in this, and we have to support that to improve our tools so that we can go to that level. So as you can see, the next would be CFET, and then 2D materials, and then conductive oxide. Everything. It is immense possibilities there. And also we are our 10 years roadmap, we are investing in the artificial intelligence, cloud network, and IoT devices, etc. So yeah, that was I was talking about, that Intel is moving like 320 angstrom. They give a different name with a thing. So that's a Intel roadmap. That's a TSMC roadmap. They're also going to the same direction. And the iMac is also going, see the nanoseed gate all around. iMac is also going to the same direction. And yeah, everybody is going towards the same direction. Any question on that before I move to a completely different subject?
Sir? So there is one question from.
Yep.
So yes, sir. There is one question from Shubham. He is asking that why do we deposit the silicon germanium layer? Can we use any other material instead of the silicon germanium layer?
Yes, you can come up with anything, but right now, silicon and silicon germanium we can grow epitaxially. So that means it's a very good crystal quality. That's one of the main thing. When you are going to 2 nanometer, you need a nice crystal quality. So on silicon, you just adding germanium 30%. So silicon is 70%. So silicon germanium epitaxially you can grow and maintain the single crystalline thing. It is not deposition. It is epitaxial growth. And second thing is, while you are etching, while you can etch silicon germanium, you are not etching silicon. So yes, you can come up with a different material. First one, you have to have a single crystalline property so that your crystal quality is nice. And second, you have etch selectivity, that you can etch one material while you do not touch the other material. So the etch selectivity, in industry right now, they're working on the chemistry also. They can etch silicon germanium while they're etching silicon just a little bit, like 90% is to 10%. So, yep. So that's the reason why you are using silicon germanium and silicon. Yep. So move on. I have only 15 or 20 more minutes. Okay, I will move on quickly. Hybrid bonding or 2D silicon interposer. So packaging is not like industry, like other packaging. Like while we are student, we used to think packaging. No, it's not that. It's a hybrid packaging. It's a way more advanced thing. Like we are like here, like Apple. Everybody is preparing their some other device. Like somebody's power amplifier, somebody's low noise amplifier, somebody's that, somebody's that. So they're coming in assembling. So in the advanced, like in iPhone 13 also, so they are putting all those chips manufactured by different companies and come up with the same thing, while still it is a small area. That's the beauty of this thing. So is hybrid packaging. And for hybrid packaging, you need test vehicle. How you will know that you have bonded properly? So you need a kind of test vehicle. It's called daisy chain. You can search in Google and later if you are interested more. I'm just going through quickly. So there are kind of metals, two metal layers, like one is metal layer 1 and one is metal layer 2. And then when you are bonding, so like this is the parent wafer. Say it's a parent wafer where you will bond. And the top one, the blue color, is the second wafer where it will come and put like bond. So those pads will bond. You see, they make a nice bridge. And now here you can touch the two pin like simply with multimeter and see, well, it is short. So that means it is well connected. The both has been bonded properly. That's called daisy chain. So it's kind of going up and down, up and down, up and down with a different thing. Anyway, so I will also give some glimpse on the copper, that why the copper is another thing industry is using. It's very important because it's way better than aluminum and less expensive than platinum. So it's definitely a high performance and with a higher thermal conductivity. But it has a problem. The challenges is it can easily diffuse into the silicon. And second thing is it is very difficult to etch. Cannot etch it chemically or any wet etching. So you have to do like CMP, chemical mechanical polishing. And that's why this term damascene comes. The term actually came from Middle East, actually. They used to do it for their sword, like the metal sword. So they used to do like damascene, and on the sword, they used to do like different scribing, nice scribing. From there, this damascene came actually. So what is that actually? So I'm going a little bit faster. So, so like on silicon, we need metal layer, right? So how we will do the metal layer? The copper is better, but copper again diffuse. So we need to protect the copper layer. So that's why we put first a liner. It's called tantalum or tantalum nitride is typically used. So it's a liner which is protecting copper to go inside the silicon. And then what we do a PVD, like a seed layer of copper. And then we will, so there is a thin layer of copper like surrounding everywhere here. And then we'll do electroplating. We just boom, copper all over, this kind of thing. And then you do CMP. So it's like a mechanical polishing, mechanical chemical polishing, and you just planarize the surface. That way, the copper lines are made. So you will see that in the Intel i7, and i5, those have 13 layers of copper layers. How they build? All this is built is that way. This is called damascene. It's a single damascene, dual damascene. There are a lot of other things. But that way, usually we make. So we put a liner first, and then we put a seed layer, and then we electroplate it, and then we do the CMP. That way we do. I mean, I have one video. Can I run that video? No, it's difficult to run the video. Anyway, so that's the, again, IDM. So this is the IBM data. As you see, as you are going on the top, it's increasing. But you see how many layers are there. So it's all connected. This is all made like the same damascene, like those things. So as we talk about the damascene, how daisy chain, how we will make the daisy chain. So first we'll just do some litho on the silicon process on top of the oxide, and then we'll etch it, and then we put a liner, tantalum nitride, and then we'll put a thin layer of copper, and then we fill it with copper, and then do the CMP, and then we get the structure. And then we do the via, it's called via, the pad. And then again, the same process, we will etch, and we put the liner, and then copper, and then CMP. So that way we will get, so this layer. So you see that structure, on top of that, there is the other thing. Now, how we will bond actually. So when we will bond, you see there is a little bit gap here. I will show you in the next slide. So these two would be bonded on top of each other. So one would be coming and bonding on top of each other. So you see, first we will do the oxide to oxide bond, which is a low temperature bond. And there's a very good bonding at low temperature. But you see there is a gap because we recess the copper a little bit. And that will, and then we will go to annihilate at high temperature, like 200 degrees to 300 degrees centigrade, or maybe 350 degrees centigrade for a long time. And then copper will expand. And these two copper will expand and join. And that way we are making a nice metal copper to copper bond. That's how we do the bonding. So you get some preliminary idea. And there's another advanced thing is TSV, through silicon via, where we can etch the silicon. So we take one substrate and which etch, and it's not much, like 100 micron, we etch, and then we polish from the backside. So we just chop the whole wafer out. We polish, first we mechanically polish it, and then we do the CMP. First we grind it actually, like, because the silicon wafer is like 0.5, 0.3 millimeter, 300 micron. And here we are doing only 100 micron. So we have to remove this 200 micron of silicon, just grind it away, and then polishing it and make it smooth. And that way you can have a whole new area, like you can bond both sides. So that's the beauty of TSV. And there it comes the silicon etching. Silicon etching is another good area in industry. It's called the BOS process. I'm just, because of the time, and I don't think we don't need to understand everything. But the advantage of CMP, TSV would be, this is the logic board in computer. So everything you can come squeeze, everything can be come on top of each other. Yeah, definitely it has a lot of challenge. And I'm just moving faster. These are not so important. So you see how the backside is made. It's a lot of those things to integrate, to miniaturize, to scale down everything nicely. One thing I would like to say, how the BOS process. This is important. You can search, and if you are interested, you can see that what is BOS process. It's a simply silicon etching, but how you will etch. So they found that SF6 can etch properly, but it is also etching the sideway. But we want to etch, like we want to trench, like a straight trench. So we will etch, protect the side layer, which is the SF6. The C4, this chemical, the same compound, the same chemical can protect the side layer, and the other chemical can etch. So it's like sidewall deposition, etch, sidewall deposition, etch, sidewall deposition, etch. Though there will be scalar formation, but that way we will do the silicon etching. So yeah, if you are interested, you can search the BOS process, and that's way we can make the TSV. Right? I'm not going in the other detail. Those are pretty much detail, how it looks like, how they like. Yeah, all you need to know. I just give you the basic idea that what is TSV and those things. And there's another thing, new thing is coming, chiplet. It's like plug and play and those things. So this is our tail roadmap that we want to put in one tool. We want to put everything. All I said, the process, like wafer process, CMP, bonding, trimming, grinding, cleaning, CMP, and then wafer process. So all this process I talked about, this is the thing we have to go through. And we would like to put everything in one single machine so that you put the two wafers and it will be bonded and come out. We have a wafer to wafer bonder. This is the wafer to wafer bonder machine, and that has a cleaning and plasma chamber. And we have another chamber for like trimming. So finally, so TEL is the company where we would like to invest more in R&D, and we are among the tool companies. We are the highest number of patent in US and in Japan, and we are continuously doing R&D with all tech giants like Intel, IBM, TSMC, iMac, and Micron, all the companies, and we strive. We have to develop our machines so that they can improve their machine. So that's the summary. So the scaling, and I showed how the device is really scaled down from the classical to the gate around, and how the packaging industry is moving. Like we really want to package a memory on top of the processor so that all the time it takes for the processor to fetch the data from the memory. So that time we are just reducing by bonding it. That has a lot of challenge. Thermal is another challenge. How to remove the heat, those will be there, but it is the mainstream following, the industry is following. So that's the end of my talk, and this is the 60th year of my company. Any question I would like to answer?
Thank you so much, sir. Yes, sir. Thank you so much, sir. It was very interesting talk. I hope participants are enjoying. Sir, there is one question from B. Suresh Kumar. He is asking that how the threshold voltage for the FinFET transistor compare with the conventional circuits.
Yeah, threshold voltage is pretty much lower than the conventional circuit. Yes. When you can go to the theory, I just showed here how to build the transistor, how to build the FinFET. I mean, if you are interested in the theory part, you can always hear. This is not the focus of this talk.
Okay. And another question is from Dr. A. Srivani. He's asking that silicon has an indirect band gap, but it is widely used in fabrication. Why?
So what is the problem in indirect band gap? I mean, we do not have any problem. I mean, the question can be asked that why in LED market or somewhere that in the indirect band gap, the direct band gap would be easier for LED, but I don't see in the semiconductor indirect band gap has any problem.
He's asking that how to deal with the heat in 3D integration.
That's another thing. That's whole new research. I mean, everybody is doing that research, how to remove the heat, because that's the main challenge. It's called 2.5D integration, 2.5D second interposer, and 3D interposer, three dimensional. That's the main challenge. That if you put a memory cell on top of the processor will heat up, and that will heat up the memory cell, and then memory cell will not function properly. That's that's a problem actually, and that's why it's not so easy, and that's why we cannot achieve that. And industry is working on that. There's a lot of mechanical professors. They are working on fluid mechanics, how to remove the heat from the processor and make it cool down. And there are a lot of other research is going on to remove the heat, but still it's not solved yet. So you are welcome to do more research on this. That's a good topic, definitely.
Thank you, sir. Now moving ahead to our next speaker, Professor Biman B.
Thank you very much.
Thanks. Now moving ahead to our next speaker, Professor Biman B. Mandal, who will be giving a talk on 3D printing and bioprinting of organs and tissues. Professor Biman Mandal is a professor and associate dean academics UG at Department of Biosciences and Bioengineering, IIT Guwahati. Professor Mandal has received his PhD from IIT Kharagpur and postdoc from Tufts University, Boston, USA. His research area is tissue engineering and regenerative medicines. Professor Mandal has over 167 publications in last 5 years, and with total cumulative impact factor of 1095 with H index of 54 and 8,300 plus citations. He has been recognized as one among 75 under 50 scientists shaping today's India by DST. He has also been included in World Top 2% Scientist list released by Stanford University, USA in 2021. Professor Mandal has been awarded as Innovator in Tissue Engineering of the Year in 3D Printing World Awards 2019 for contribution in 3D bioprinting of human organs and tissues for transplantation. Before we start the talk, participants are requested to mute themselves and post their queries in the chat box, if any. Now I request Professor Biman sir to enlighten us on the topic 3D printing and bioprinting of organs and tissues.
Yeah, thank you. Very good morning. Am I audible?
Yes.
Yes.
I'm getting a feedback. Just a minute. I can hear my own voice. 1 minute. Hello. Can somebody mute the speaker there?
Yes, sir.
Yes, sir, it is muted here.
Hello. Yeah,
Can
but
you
I
hear
can
us?
hear my own voice actually.
Can you hear us right now?
Yeah, I can hear you, but I can hear my voice as well as a feed.
For us, it is trouble-free.
Yes, we are not.
We don't have any echo in this side.
Yeah, I understand. Am I audible now?
Now you are not audible, sir.
Just a minute.
Sir is muted, maybe he's trying to.
Hello.
Yes, sir.
Yes.
Yeah, I have to solve this problem. Let me reconnect. Okay.
Sure, sir. Participants, kindly wait for 2 minutes till sir try to reconnect with us.
Hello.
Yes, sir, you are audible.
Yes,
Now
sir.
it is resolved. Thank you. Yeah, actually, I was probably logged in 2 devices. That's why I could hear my own voice. Yeah. Let me know when the slides are visible to the screen.
Yes, sir, slides are visible.
Okay, thank you. Thank you, and a very good morning once again. I'm sorry for the glitch. The technology sometimes beyond our control. But anyway, so first of all, thank you to the organizers for giving me this opportunity. And as has been said, I belong to IIT Guwahati, and basically I'm working on the area of organ printing and tissue regeneration. And we use a lot of techniques, and particularly we use the technique of 3D printing and bioprinting for organ and tissue regeneration. And that is what I'm going to take you through to the rest, I think 50 minutes or so. Now, my association primarily is with the BSB department, which is Biosciences and Bioengineering department. I'm also associated with the Center for Nanotechnology and the School of Health Sciences and Technology. And as I said, we look at how humans can regenerate. Of course, the concept of regeneration is time immemorial, and we have read, we have heard about regeneration. We have heard in novels, in movies. We have looked at how from a single cell, an entire human can be regenerated. And that what we talk about is the stem cells. And particularly, if I have to take you through, and we all have read about the movie Harry Potter, and where there is a particular saying, we're rising from the ashes. And what they talk about is even a single speck of ash of the bird phoenix, is allows it to rise. And that is exactly what happens and is possible in humans as well. And that is what we look at in terms of using stem cells. Also, I would like to briefly take you through some life experiences which we do at times ignore, particularly tadpoles, planaria, annelids, amphibians, lizards particularly. If we touch the tail, we have observed that tail falls off, and with time, maybe in a couple of weeks or a month time, the tail grows back, and same thing happens with the limbs. And that is exactly what researchers are trying to understand, how this regeneration happens, and how we as humans can probably exploit that part, and try to by trying and understanding and recreating these niches so that the lost organs and tissues can be regrown back. Now, this has quite a lot of importance in terms of our health and well-being. And we all are aware that the current source of organs and tissues are donors. And we also are aware of the number of donors of these organs and tissues are very limited. And we are somehow hesitant in terms of donating organs. But again, there is a huge queue of people who either have a diseased organ or a damaged organ who are waiting for a donor to save their life. Now, again, as we understand, there is a huge gap between the supply and the requirement. And one such area which could probably help us to engineer these organs in the laboratory is the concept of tissue regeneration and tissue engineering using stem cells and biomaterials. And that is exactly what we work on. Now, before I take you through to some of the examples of organ regeneration and tissue engineering using 3D printing, bioprinting, and other allied technologies, this is a gist of the technologies that we have developed from the laboratory. And besides, you'll see the names and the faces of the students who have contributed in terms of developing these technologies. And we do extensively work on various soft and hard tissues. For example, we work on liver regeneration, we work on blood vessels, we work on how to create bone grafts and take care of damaged bones so that life can become easy. Then also we look at skin and wound care. We look at smart delivery of molecules for cancer treatment. Look at artificial pancreas, cardiac patch, and so many and so forth. Now, as I said, to many of you, understand the audience is a mix of biology and majorly non-biology. So I will, without using much technical jargons, I'll take you through to probably understand this particular field and also probably introduce you to how 3D printing and bioprinting is shaping the world today in terms of addressing this unmet requirement of tissues and organs. Now, if I have to present to you tissue engineering, this is a slide which is a gist of what we do and how we do. And if you look at the slide, you have the left-hand side panel where we have different kind of cells. So if you look at the human body, the human system, it is made out of organs and tissues, and every organ and tissue is made out of cells and extracellular matrices, which is cell secrete, and that constitutes a tissue or an organ. Now, if we are recreating that, or if we are creating that, what we need is the cells, and these cells are very diverse depending on what are the tissues and organ types that we have, and they have a very specific functionality. If I have to give you an example, liver cells, if I have to say liver cells, they have very specific functions in terms of metabolizing compared to maybe a bone cells, which have very specific functions in terms of giving shape, structure, and resilience to the bone that we have. So the functionality are very diverse. So the first understanding is what kind of cells we use. So we use primary cells, which can be extracted from the tissues itself. For example, if we are creating a liver or an organ like a heart, we kind of have the option of taking the cells from the organ itself. Then what we do, and also we have the other option, which is called the stem cells. Many of you may have heard about this stem cells. These stem cells are, as I was saying and introducing you in the beginning slides, are progenitor cells, which have the ability to recreate any kind of cell types by differentiation. It's like changing morphology and shape and function. So they can be like any kind of the cell. And also one very unique feature is they keep on have their reservoirs in the body. So we have these stem cells located at different locations, and we can actually tune them to differentiate and behave like some specific cell types. So we have these two specific cell types which is required. Now, once we have the cells, what is required is to expand them or grow them in plenty. So maybe I'll use a pointer. Yes. So to grow them, we use cell culture. Now, cell culture is a very specialized technique where what we do is the cells have the inherent ability to divide. From one cell, it becomes 2, 2 to 4, 4 to 8, 8 to 16, and that is how they expand. So what we do is to grow them in plenty, and that is called cell culture. Now, why it is required? Because if say for an example, if there is a donor who donates certain cells, or even if the same person, there is a biopsy or a small portion of the tissue taken, the cells can be extracted through processes, and those small number of cells can be expanded to grow in number so that they can be used for engineering organs and tissues for the individual or for any other individual. Now, after that, what we require is the concept of the using a template or a scaffold, and this is where the science of biomaterials come into the picture. Now, what is very unique here is the understanding different kind of materials, how each material have their unique properties, which would guide these cells to attach on them, to grow on them, and allow them to function. They act as a template. So what do I mean by a template is, for example, these cells which were grown in 2-dimension or a petri dish, they cannot form 3-dimensional structure by themselves, even if I give nutrient and the right conditions. So what is required is a template, which is by this biomaterial, and this template has certain properties. The properties is it should be amenable to be tuned into an organ and shape of an organ or a tissue, and the cells grow on it. And with time, the material is going to degrade out, and what would be left out are cells and their own extracellular matrices, and the organ would be regenerated. Finally, they would be matured in a bioreactor. A bioreactor is a device which allows replication or creating certain environment like forces and flow and some specific conditions. What we have is as a dynamic condition. It is matured, and then finally it is to be transplanted to the human being once matured. Now, as I was telling you, probably I'll take you through because of the audience. You may not be aware of certain cells and the requirements, so I'll just take you through. So as you can see, these are all individual cell types. And as you can see, the cells actually, they are mobile. They are adherent, they are sticking, and they stick to surfaces, and that's how they form a 3-dimensional structure. Also, they are very, very choosy in terms of their requirement of media, nutrition, and growth factors, and many other things. So as a researcher, as a bioengineering researcher, we have to understand how these cells behave, what are their specific requirements, and how they can be grown in number so that their functionality is retained, so as that particular organ to be made a specific in terms of the functionality. Also, as I was saying, the scaffolds, which are 3-dimensional structure, imagine this is the scaffold and these are the cells which are seated on top of it. What happens is when the scaffolds have certain properties which allows these cells to grow and proliferate inside them. So this allows them to grow and proliferate, and through their pores and the interconnectivity that they have, and that is how the tissue is replicated with time. As I was saying, this bioreactors helps in recreating different kind of physical forces. So what I'll just give you an example. So when we are born, our bones are not very rigid and strong, and that is why we do not, as human beings, we do not directly walk. What we do is we take small movements in the initial months, then we crawl, and then we stand up, and then slowly we start to walk, and that is where the bone gets developed and matured. And this crawling or standing or smaller exercises and the nutrition allows this bone to be densified, and these physical forces or the stresses that it receives what allows the bone to mature. And this is very, very important because our system is a dynamic system, and this dynamic system has to be replicated if we are replicating any organ or a tissue. Now, the most important part, what we try to have as an USP is, in terms of creating these organs, is form follows function. Now, form follows function means a specific form which not only replicates the internal, the external morphology. For example, if I'm making a car engine or a car, it should not externally look like a car, but internally it should have the required parts and the dimensions so that the functionality of a car can be attained. And same thing for the organs. It is not the external morphology, but the internal architecture in terms of cells in their right positions, in their right orientation, that allows this physiology to happen. And that is called form follows function. If we are recreating the form perfectly, the function would be attained to near perfection, and that is what is understood with time. So in this direction, we are looking at all the tissues that we are creating. Now, to introduce you to the materials that we use, as I was saying, there is a requirement of a template or a scaffold, which is called a scaffold, and it can be made using different kind of materials, be it natural, be it synthetic. Every material has its own advantages and disadvantages. But what is required for a material, as I said, it should be amenable to be made into different forms so that the cells and the tissues can be created, and it should give some biological, biochemical, and biological signals for the cells to grow, proliferate, and do their function. And this is where we used uniquely silk. Now, silk, we all know, you all know, is a textile material which is made for making apparels. But this silk is nothing but is a protein. And this protein is made out of amino acids. These are the building blocks. So what is the beauty of this material is this material, as I said, is made out of amino acids. So it's a protein structure, and when it degrades into amino acids. So in the body, it is much easier to make a degradable system so that the cells can make the structure and the material can go out. It has many other specific properties. But before I go into that, just give you a glimpse of, there are two kinds of silk. One is the mulberry silk, which is as the South silk or the China silk. It is domesticated, and it has its own unique properties. The other type of silk is the null mulberry silk, which is the wild silk. And we at Guwahati and Assam are very popular destination for this kind of silk. And India is very rich in this with various endemic silk, which are null mulberry silk. And we do work on Muga, Tasar, Eri, and these are the wild varieties which grow outside in the farms. And also they have a very unique property. This type of silk has a certain RGD sequence. So just to simplify this, these are very specific amino acid sequence where the cells would love to sit and attach and proliferate. Meaning, it's like if I'm making a structure where I want the cells to adhere and divide much better for a better organ formation, this already has that sites which allows the cells to sit, and that is a very unique property. And it is much advantageous compared to the other materials that are available. Also, it has many such advantages. I'll just quickly take you through. So as I said, silk is a protein, and it is one of the materials, particularly Bombyx mori is a FDA approved material. So Food and Drug Administration of USA has approved this for clinical use. Now, why I am putting this, if you are a biologist, you would understand, and even a non-biologist, you should understand that our human system is very protected by the immune system that we have, right? So anything which is going inside has to be accepted by the body, the immune system, so that it is not rejected. That's very important. And also it should be compatible to the organ system that we have. It should be non-immunogenic, meaning it should not create an immune response. And as I said, it should be degradable, and it has already RGD size. It is much easy to process, abundantly available, and inexpensive. The last three points are very important in the context of India and developing countries, and also in the context of making affordable technologies. My laboratory is trying to have these technologies in an affordable manner so that these organs can be recreated at a much less expensive cost, so that it can reach to the last mile, who are in need of this kind of organs. Otherwise, there are materials, for example, collagen, which is gold standard materials, but they are very expensive, and they are maybe more than 1,000 times more expensive than a gram of silk in the pure form. So if the material cost comes down, if the processing costs come down, automatically the organ concept of organ regeneration and tissues regeneration would be much affordable, and it can reach to the required audience for saving life. Now, before I take you through the examples, a quick glance on the different techniques that are used. And I'll be giving you more details about 3D plotting or 3D printing or bioprinting separately, but there are other techniques also which are used for making these kind of tissues and organs. To simplify, I'll explain this. So as I said, form follows function. So the form has to be replicated, and different organs and tissues in the body have different forms. And if you look at under the microscope, they have different structures. Some are very strong, rigid, with very high pores. Some are with very less pores. Some have specific orientation and they are in nano dimension. Some are in micro dimension, and so henceforth. So if I am replicating an organ of that particular tissue or no, the cell type for them to adhere and grow, I have to use technologies so as to replicate that particular form, and that is where the techniques are used. Now coming back to the point of today's topic majorly is, of course, I'll be taking you through some non-bioprinting examples as well. But 3D bioprinting or 3D printing is very unique, and many of you may have heard the term, where it is an automated process. What it does is any shape, any structure, any physical form, entity can be created using this technique. How? So there is a scanner. So if, for example, I want to make this particular shape, what I can do is I can take the scanner and scan the image, and there can be layers of this image slicer that can create these slices. I'm trying to simplify this for the audience. And then what happens, this design is fed into the computer. Now, once it is fed into the computer, what we have is a material. So if it is 3D printing, it is a polymer which is printed in fine dimension in the range of micrometer, and one can replicate this particular tissue and organ exactly precisely. But if it is 3D bioprinting, so the difference is, because it is 3D bioprinting, what it prints is biological cells. So in 3D printing, we can use heat as extrusion-based method, where the polymer is melted and one can draw fine wires and create these structures. But in living cells, the problem is they are very sensitive to temperature. They required a certain specific environment to grow, and they are sensitive to shear and many other forces. They would die. The cells would die. And we have to keep the cells sterile, and many other things have to be taken care of. That's why bioprinting has a very unique material, which is called the bio ink. So what is this bio ink? This ink is a gel which has a very unique property. It is a gel with the cells inside the nozzle, and once it comes out of the nozzle, it forms a gel, solidified gel, and it can be made solidified by using chemical curing methods, light, and enzymatic methods, and many other methods. These are very unique, and they are compatible for making these kind of organs, this kind of technologies. Now, this is a glimpse of the structure that I am trying to create. These are the CAD slices. This is the slicing, which is fed into the computer, and this is the machine which has created the replica of the dimensions that I have given. And likewise, this 3D printing and bioprinting has not only revolutionized the commodity sector in terms of creating different architectures and forms and other things, but also it has revolutionized creating to create biological substitutes in terms of organs and tissues to save life, and that is the very unique property. Now, I'll take you, as I'm saying, I'm going to take you through some of the examples, where we have, either in full the bioprinting or in partially bioprinting techniques, along with other non-bioprinting techniques. So this is the first example, is creating bioengineered blood vessels. Now, water blood vessels, we all know these are the highways in the body where the oxygenated blood with the oxygen is from the heart, it goes to the different parts of the body through the arteries, and the vein carries the deoxygenated or the spent blood to the heart for oxygenation, right? So what problems arises is occlusion or deposition of cholesterol or fats in the artery, and this, what it does, as the video is showing you, it clogs the flow of the blood, and because of which secondary complication arises. Now, as I was saying, this is a typical, starting point for heart attacks through, this atherosclerosis, and then what as I described, technically happens is a deposition of cholesterol within these channels, leading to blockage of the blood flow, as you can see in the video as well. Now, there are different methods and technologies that are available, which one can use, doctors use. Either it can be balloon angioplasty, vascular stents, which is nothing but to open up the blockage, and these are temporary measures. But again, in case of bypass surgery, as you may have heard, when there is blockage in the coronary artery, so what happens is the doctor would advise for a open heart surgery, and that is where this kind of designed or lab-grown bio-engineered blood vessels come into the picture. So currently, what is used is a vein from the leg, and it is replaced as a bypass. That's why it's called a bypass surgery, and bypassing the clogged coronary artery, and this is done to save the life. Now, because that has secondary complications, because there is a vein is carved, but again, a heart is replaced with artery is replaced with a vein, and so many other physiological complications arise. And there is of course no donors available for this kind of applications or requirement. So there is a huge requirement of small diameter blood vessels. So I'm going to simplify this. I'm not going to take you through the biological hardcore experiments, but what my intention today is to show you how this created printed blood vessels, which are having the shape of a blood vessel. What is a blood vessel? It is a tubular structure. It has some specific properties in terms of the lumen. It has some properties which are like it should not burst out in the blood pressure, that high blood pressure that it has. It should not clot the blood when it runs through the blood, the artery, right? And it should not create any immunogenic response once it is implanted. So designing was a complicated task for this. So we designed this type of arteries using material, silk material, and we implanted them into the animals. Now, if you are a non-biologist, if something is meant for human application, it has to pass through stringent clinical testing, be it the laboratory testing or in vitro testing, we call it. Next is the animal testing or the in vivo testing. Then comes the third, the clinical trials, which is on the humans. And then if all goes good, then it comes to the market as a product. Now, the intention here was, as you can see in the diagram, is there is a blockade here in the artery, and we removed that, and then we implanted our blood vessel here, and this was done by surgeons, as you can see in the video, the surgery. Now, what happened is, just quickly to take you through, what happened is in the ischemic, as you can see, there was a blockade, and it was replaced with this artery. Now I'll show you a video here. First, I will show you the occluded video here. Just a minute. So this is a video which has occlusion. So just to see the occlusion, there is a dye which is injected into the heart, and there is a black dye which goes, and you can see this portion, this dye doesn't move, meaning there is a blockade here, and that is how it blockade in the body, in the arteries, it is identified by doctors. Now, if there is a blockade, we have to take care of this blockade by removing this artery through a surgery, and that is what is done. And in this surgery, after this surgery, what was implanted is our blood vessel at the particular site. And now you can see when this dye is injected, this dye clearly flows out, and this is the site where the artery developed by us was implanted. So, and also after implantation, we did a long follow-up for the animals that we have used, and we have found them to be compatible. They are very patent, and there are certain properties which are required. For example, the doctors would stitch them at the site of the native tissue. So there is this artery, and there is this particular region where it is blocked and it is cut out, and this artery has to be stitched back. So stitching, it should be amenable to stitching. It's called patency. It should be amenable to not clotting the blood. And finally, of course, the function should be restored back, and that is what we have shown in our study. The second example, what I'm going to take you through is 3D bioprinting work, is beating cardiac patches. Now, heart, as we all know, is a pump in the body, which allows or which pushes the blood to different sites of the body of oxygenated blood, and its function is very, very important. And if there is any anomaly, what rises is a myocardial infarction or MI, what is commonly known as the heart attack. Now, it is because of certain reasons. The reasons are that in the heart, and if this is the diagram of the heart, let me pointer. Yeah. So if this is the region of the heart, there are, because of lack of oxygen and other region, there is damage to the tissue, and this tissue is made out of cardiomyocytes. So they work on the electrical signals which arise from the particular node, and that is how the entire heart starts to beat. Now, because there is a dead tissue here, what happens is this leads to arrhythmic beating of the heart and leading to cardiac arrest or the heart attack that is popularly known as. Now, what are the potential solution for this? The potential solution is initially stem cell therapy was used, where stem cells, which has the ability to, these are progenitor special type of cells, as I said, has the ability to differentiate to heart-like cells. And what the doctors would do, they would inject the cells as a stem cell therapy, and the cells are supposed to be going and residing in this place, differentiated to cardiomyocytes, and the lost function is retained back. Now, the problem, what happens is, the cells, once injected after the stem cell therapy, do not reside. Most of them, they are lost in the process, and many die, and and the functions may not be entirely regained back. And that is what is the complication. So what was thought is, can we create a beating cardiac patch? It's like a band-aid, and what can be put at the site of the dead tissue or the dead region of the heart, so that the function can be retained. So before I explain this, probably I'll go to the video first. So to explain and better understand, so this is a cardiac patch. It is the size of a stamp, right? And it is nothing but a band-aid, but has a very unique property. So what the property is, this is made out of cells using 3D bioprinting. And what it does is, the cells, being cardiomyocytes or heart cells, they beat, and the entire construct beats. So what is the reason for this to be made this way? As I said, the heart is a beating structure. So if I am replacing a portion of the heart with a non-beating structure, then again it doesn't solve the problem. So it has to be a beating structure, beating in a way which is similar to the human heart rate, and to attain functionality and take care of the myocardial infarct region. Now comes the how we do create this. So without much technical jargon, I'll try to explain. So heart is made out of cardiac tissues, right? And these are, as I said, these are involuntary cells which through the receiving the electrical signals, they beat, and they beat at a certain rate. And that is how the heart functions. Now, the patch what we created is using a 3D bio ink, which is made out of silk and some other additives to it. And what we did, we added, and we created two kind of inks. One kind of ink should be able to carry cardiomyocytes, which were developed from stem cells. So stem cells we differentiated through some special procedures to cardiomyocytes, which are electrically beating cells, and they beat as I showed you already. So all this green that you see are the cardiomyocytes or the heart cells, which are growing in the 3D printed structure. Another thing that we did was to create blood vessels. Now, just to explain why we did it, any kind of tissue in the body, if all the tissues in the body, they need oxygen, nutrients, and these blood vessels bring this nutrition and oxygen to the site for their survival. Now, if we create any structure which doesn't have these blood vessels, what will happen with time, they will become dead, and to keep them alive we have to create blood vessels along with. So what we did was, these blood vessels are nothing but a special type of cells which are endothelial cells, and they have the ability to differentiate and make these blood vessels. So what we did, we created another ink where we created endothelial cells or the blood vessel cells, and these are marked as red. So what we did was we created alternating layers of cardiomyocytes or heart cells and blood vessel cells, and that is how the entire construct was made. Now, what is the bottom line here is the material should allow the cells to survive, the heart beating to attain as a physiological function. It should surviving for an extended period of time. Most importantly, they should beat. And once we check the beating, this is the figure which shows the beating rate. So we achieved 73 beats per minute, which is very close to our human heartbeat rate of 78 to 80 beats per minute. So that was a very unique proposition. Of course, I'm trying to oversimplify this, but there is a lot of science that goes into creating such functional tissues for organ regeneration. So what is the whole idea is? That we can create these structures, and this would be used by doctors through surgery to be applied onto the myocardial infarct or the dead cardiac tissue, and the functionality would be retained and the patient's life can be saved. Also, they have a very specific function. One you must have heard of: babies are born with a hole in the heart, and that is where the oxygenated blood and deoxygenated blood, this gets mixed, and there are other complications. So this kind of beating structures can help those kind of kids, and they can be used to plug the hole and not allow this mixing of blood to happen. Then they have enormous other applications as well. So we are doing animal testing, and to take it forward. Third example, what I'm going to give you quickly, is using printed materials and silk materials to take care of diabetes. Now we know that India is the global diabetic capital, and also majorly primary reason is because of our food habits and and many other reasons. And as we know, diabetes is categorized into type 1 and type 2. And here we are looking at, of course, type 2 can be more controlled through lifestyle. But type 1 is autoimmune disease. So what is autoimmune disease? Is our own cells, immune cells, what we have in the body. What happens is they attack the cells which create insulin in the body. And the organ that houses this is the pancreas. So this pancreas is a specialized structure. They have specialized cells which produce insulin, glucagon, and some of the hormones which regulate our glucose level in the body. And that is how we could control our glucose level in a day-to-day basis. And if this order or homology, homeostasis is disturbed, then there is disease that comes. And if what happens is this, through autoimmune disease, immune cells kills these beta cells which produce this insulin, and because of which there is non-regulation of glucose, and that is what we know as type 1 diabetes. So what is the treatment? Of course, there are injections, insulin-based injections. So the patient has to check their blood glucose level, and based on the glucose level, they can take shots of insulin and to regulate blood glucose level. So that was the problem statement for us. So what we decided was, can we have a bioengineered construct which can probably take care of this kind of patients, so that this individual shots of insulin may not be taken by them, but this body can produce its own insulin and give relief to the patients. I'll not go into the technical details, but quickly I'll explain one thing. As I said, our own cells. So imagine this is the construct that is created, or the pancreas, where we have these special cells, different kind of cells which produce insulin and many other hormones. What happens? Our immune system, different kind of immune cells come and attack and kill this. So what the proposition was, can we create a structure where we would grow these special cells which produce insulin and glucagon and other things, and protect them through a membrane. So what happens? This membrane would be semi-permeable, meaning it's selectively permeable, meaning it will not allow this immune cells to come and attack and kill these cells. but it would allow this what is produced inside insulin to go out and also oxygen, nutrient, glucose to go there because it is required for the cells to survive. And if you can implant this at a local region in the body, then they could able to be accepted and produce insulin. What was the problem statement? So after a lot of experiments, a lot of trials, what we have now developed is a simplified form of this particular concept, which is can be delivered through injection. So what happens, I'll just quickly take you through. So this is a material which is made of silk plus other combination materials. It has these special cells which are producing insulin, glucagon, other hormone types. They are mixed with this special cell, this special polymer. It has a very unique property. It can be injected at the site, and once it goes inside the body, it forms three-dimensional scaffolds. And what the unique property is, it starts to get the nutrition. There is angiogenesis or blood vessel formation, and it starts to secrete insulin. And we did a lot of studies to understand how these cells can survive longer, and also we have proved the insulin is produced, glucagon is produced, and functionality. So what I'm trying to tell you is a basic concept where the concept, success only relies on the functionality is achieved. So we checked various parameters. I'm not going to take you through all that, but what the cells has been included, they were creating insulin like what we require. They were surviving for an extended period of time. Also, they were responding to the glucose. There is two type of glucose levels, fasting and after food. So this cells has to be very fast in terms of understanding and responding to that. That was very unique. So our cells also are responding. Now we have a structure which can carry this insulin producing cells. So the whole concept is we tried in animals where we have created a diabetic animal. We injected our system and we could regain back normalcy of the animals in terms of the blood glucose level after our system was injected. So that kind of demonstrates that this is a proof of concept which is successful in at least in the animal in the lower group for a shorter period of time. We are working more towards how this can be employed in humans in the long term, so that in synthetic insulin shots may not be required, and a patient can go to the clinic, take one injection at the belly region, in the tummy region, and that would produce insulin for maybe many years to come, till the cells survive and the constructs remain viable. So making life easy for those kind of patients, and that is what's the goal of this particular study. So all the technologies that we have developed, we file patents. We have some of them have already been granted, and we are taking it forward. The next example quickly I'll take you through is wound healing and skin grafts. So basically, we all know that we have the skin and the wounds that come on the skin, and also we are worried about burning of skin, burn patients, third-degree burn patients, and so henceforth, and diabetic foot ulcer and whatnot. So what very unique thing about the skin is it heals itself, right? But that depends on what is the size of the wound. So in this case, the concept was to prepare a technology which would allow non-healing wounds to heal with time and in a faster manner, in an efficient manner, and also 3D print skin for burn injury patients, third-degree burn injury patients, so that their charred skin can be replaced with the normal skin for obvious purposes, in terms of replacing with the dead tissue. Now, for the first one, we developed an injectable version of this gel, which has very unique properties that it heals and it regains back the skin in the diseased or the cutout region very fast, and the grown skin that it helps to develop is very mature in terms of the different layers of the skin. I'm not going to the technical part, but what it allows is it allows to heal the skin very fast. it develops coloration, appendages in terms of the skin follicles, in terms of the hairs. And most importantly, what it does, it is a scarless healing. So what it allows is no scarring, even if the wound size is big, and in diabetic foot ulcer also, and in normal cutaneous wounds also. We have done the animal studies, and we have found that this method and this technology really helps in recreating back. Also, what we have, as I said, we have a 3D printed skin that we are working on, and that is using 3D printing and a bioprinting of biopolymer, and where we are recreating this skin, which would be used for third-degree burn injury patients. Also, it has a very unique application is in terms of screening bioactive molecules. For example, as you must be aware, that testing of molecules or pharma molecules in animals is banned for cosmetic products. So now any kind of cosmetic products which are applied to the skin has to be tested, and how it will be tested. So this kind of in vitro models or skin models would be used by the companies, pharma companies, to test their molecules and find out whether they have efficacy and permeability and many other regenerative ability and all that. So now currently we are working on a very unique concept of a device-based regeneration, wound regeneration, which allows regeneration of the wound or healing of the wound through electrical signals. Okay, so two couple of more examples quickly I'll take you through. One is the bioprinting of intervertebral disc, or the IVD. As the name says, it is between the vertebra. So we have this vertebral column, and because of injury, popularly known as slip disc, because of various physiological stresses, there is an injury, and this is nothing but is a cushion-like structure, soft tissue, which has two regions, nucleus pulposus and annulus fibrosus, and basically it acts as a cushion. So what happens is, because of damage to this intervertebral disc, there is excruciating pain, and popularly known as slip disc, and the doctors had to operate it and either treat it or replace with something which is like ceramic or metal. And that is where our concept came. Can we create this 3D printed intervertebral disc for patients to be replaced with a similar kind of functionality? So to cut it short, this is the 3D printed dimensions of the intervertebral disc. So now the concept is using this 3D printed. So what it has this unique design, which is the dimension of the patient's intervertebral disc, which is got damaged. It can be created in less than half an hour, and using cells of the intervertebral disc or stem cells. It can be matured for a couple of weeks in the bioreactor, and then it is ready for transplantation to the human patients, right? So that is what we have come to this stage. We are now doing animal experiments and trials for better understanding of this structure, so that it can be reached to the market for taking care of the patients. The last, I think, is an example of knee meniscus. Also, this is a soft tissue which acts as a cushion-like structure. So it is between the long bones. So what happens is, this C-shaped structure, which is a cartilaginous structure, it gets damaged because of injury. And I'll give you an example. Sports players like footballers and others, you must have heard that during dribbling, tackling, this problem happens. And also in old age, because of osteoarthritis, this gets damaged. And what is the current solution? The doctors would treat them, or they would replace with a synthetic material, but that is not something which is amenable, and there is a requirement of a better graft or tissue that can be created in the laboratory. And that is what we started working on, and understanding the physiological parameters and the architecture. What we have created is a 3D printed meniscus, which is exactly the shape of the patient. So just to quickly take you, what would be the scenario? So imagine a patient comes to the clinic, his meniscus would be scanned, the damage would be identified, and then the dimensions would be fed to the bioprinter, and the bioprinter would print a replica with the biological cells, mature it for a couple of weeks, and then it is good to go to be replaced by the doctor through a surgery. We have done all tests in terms of understanding the mechanical, biological consequences of this, acceptability of this, so that it is accepted by the body and not injected, and the patient's life can be made better. So this last is a smart delivery of cancer drugs, and we call it smart targeted delivery. So using the same concept of injectable gels, cancer drugs are creating havoc not only because of the disease but also because of the side effects. So the purpose was, can we release these molecules at the tumor site and only killing the cancer cells, not the other residual cells which are around, and can be very less side effective and toxic. So that was the potential. So we have developed this technology, and you can see, just I'll give you one example here. Just if you look at this panel, these are the tumors, and this is our using technology methods. This is the size of the tumor that got reduced. So what is the big advantage of this is they can be injected at the site of the tumor. It takes care of the tumor by reducing its size. It prevents the recurrence, which is a predominant phenomena what is observed in cancer. And most importantly, it is taking care of the side effects by killing only the cancer cells and making the patient's life much better. Just a glimpse of and today's technology. I'm not going to through much into this. These are all devices which are alternative to organs and tissues. So in today's time, what we are also looking at is how we can create organ on a chip, so that this can help in testing pharmaceutical molecules and making and understanding the pathophysiology as well as treatment modalities easy. So this is a gist of the cover pages that you have come out. These are some of the media highlights. BBC has made a documentary on the work that we have done. It is available on in Google. You can check it. Some of the media highlights. And what is very important for us was to realize what are the technologies and what are the requirements. And we're trying to address some of them with the means and modes that we have. And at the end of the day, what we do is we work in unison with industries, and to understand and also to translate into technologies. Many of these technologies have already been translated to the industry, and we have licensed them to the industry, and some are in the process, some are in trials, and the whole purpose is to bring some sort of relief to the patients who are in immediate requirement of this kind of grafts and implants. And just to end, I'd like to thank my entire team who have contributed to this particular work that I have shown. And of course, thanks to all the funding agencies and the collaborators with whom we do collaborate for executing this technologies and learning from them, and make them learn what we are good at, and that is how we move ahead with. So this is of course IIT Guwahati, and I would be happy to take questions. Thank you very much.
Thank you so much, sir. Now we are moving ahead to the query session. So the first question is asked by Sarna Roy. What are the materials can be used for bio-ink? Is there any commercially available bio-ink?
Yes, so materials, as I said, bio-inks are very diverse depending on what is the purpose. So for example, collagen bio-ink, silk bio-ink, chitosan bio-ink, like that, many materials, combination materials are available commercially, as well as one can make in the laboratory as well. Our laboratory makes many of these bio-inks because this is a very niche area, and we have 9 of those bio-inks that we have made, and we are very soon commercializing them as well.
Next query is by Richa Mishra. Thanks for sharing your wonderful work. What is the resolution of the 3D printer? How could I access or collaborate? I am working on microfluidics platform for drug delivery. Richa is from BIT Mishra.
Okay, thank you. The resolution, so now it's a very unique, a very important question. So as of now, the resolutions are down to 150 microns, but there are machines which are now come to the market, which has down to a couple of microns. But again, the limitation is you cannot use the cells for all of them to be printed, but for polymer printing, you can use them because the cell has a specific dimension. And if you reduce the nozzle size to very narrow, what will happen? A lot of shear would be produced and the cells would die. right? But again, there are printers that are available with a very high resolution for printing and 3D printing as well. And we'd be happy to collaborate with any like-minded person who feels we can add value to their work, or maybe they can take, maybe we can be of some help. So please reach me over my email, and I'd be happy to take it forward.
Thank you so much, sir. This was the last question. Thank you so much for the informative talks.
Thank you. Thank you.
One more question, sir.
Sir, there is one more question if you can take.
Yeah, please go ahead.
Is this printer applicable only for biomaterials, or we can print some other ink like 2D material ink or chemical ink?
Yeah, so these printers can be used for any kind of materials, not only biomaterials, as long as they can be printed from a liquid flowable state to a solidified state, either heat or any chemical method. I think it can be done.
Vivek has asked how 3D printing will help us in place of CAG or stenting.
In place of
CAG or stenting.
Stenting. Okay. So stents are typically made either through molding process. Now 3D printing is used to make those stents as well. So 3D printing is a technique which can allow creating any kind of 3D forms and complex forms for various applications. It can be used for making stents as well. Right. So, but stents are devices which are for specific functions. In this case, what I showed in blood vessels for removal of occlusion. So 3D printing can be used for making those stents and any other materials as
well. Can magnetic nanoparticles used for cancer? What are complexity involved in this treatment? I want use microfluidic for device or drug delivery using magnetic nanoparticles.
Yes, magnetic. There are lots of papers which researchers have used magnetic nanoparticles. The whole concept is to use, our external magnetic force to direct this for targeting of this to the tumor site. But again, it has its own advantage and disadvantage. Advantage is one can probably, hypothesis is it can direct to the tumor site specifically. The disadvantage is that if this tumor is available at a lower depth or high depth, then the magnetic field may not be effective. Also, the magnetic particles may have their own cytotoxic effect, and unless properly evaluated, and so many other things, right? So one has to not only the treatment procedure, but if somebody is using biological procedures, one has to understand the compatibility and the clearance part as well. So immune consequences, clearance of those, so all those are into the picture rather than only the application part. That's why biology, applications are so important, so interesting. But one has to have a 360 view of the advantages and the disadvantages as well. But it can surely they have a good prospects and can be used for biosensing and many other applications, in vitro applications as well.
Thank you so much, sir. This was the last question. Now we'll be taking a tea break.
Thank you.
Participants can join by 11:45. We'll be taking a tea break.
Welcome back again to the session. Moving ahead to our next speakers, Dr. Taikang Wu and Dr. Hen Chen, who will be giving us on the topic talk TFTs in the display technology. Dr. Taikang Wu graduated from the University of Missouri, Columbia with a PhD degree in chemical engineering. He owns more than 20 patents. He has been in the display industries for 35 years. He was the project lead on the thin film technology development of TFT LCD in Taiwan. He was involved in G2.5 TFT LCD and G5.3 construction project. He worked for AUO as the general manager and VP of Mobile Display Business Group and then to the position of Chief Intellectual Property Officer. He is now an independent consultant from 2020 and also a member of Phi Tau Phi Scholastic Society.
Mr. Heng Chen graduated from the University of Cheng Kung with master's degree in mechanical engineering. He has been in the display industry for 25 years and has experience of establishing accumulates 6 fabs in career till now. He was designated by AUO as the task force team to transfer TFT LCD technology from IBM Toshiba and built G3.5 in Taiwan. He was promoted as G5 fab director and led a fab team to develop TV products by introducing wide view angle, vertical alignment, and one drop filling technology. He was the vice president of a subsidiary company of Foxconn Group, and currently he is an independent consultant. Now, before we start, the participants are requested to mute themselves and post their queries in the chat box, if any. Now we request the speakers to kindly start the talk. Over to you, sir.
Thank you. Good morning and good afternoon. There were very few electronic technology not being obsolete after 50 years. Silicon semiconductor is one, and the TFT LCD is another one. In this talk, we are going to do the investigation. Where we can see the next slide.
Yes.
And next slide, please. Yeah. Okay. In this slide, in this talk, I will review the breakthrough and the improvement, and the technology structure of TFT LCD, how the evolution can be taken place in different aspects. And the third one is the physics versus perception, the nature difference between the semiconductor versus the display. And that's one very special thing is a heterogeneous integration has been a driving force for evolution in TFT LCD is actually in semiconductor too. In the summary, in return of the invest in display, we are invest our future. Next one, please. Next slide, please. Yeah, I think iPhone, as everybody know that iPhone from 2007 have changed the way of living for human being. Advanced silicon inside and outstanding display outside. Connectivity in the air. It forms the legend of iPhone. It is a very interesting example of this scientific interaction we can see from the iPhone legend. The upper side is about the Apple Silicon. The lower side is about the display. And iPhone 4 start with A5 chip by 45 nanometer process in 2011, and end up by the updated one is the iPhone 14 with A16 chips by 4 nanometer process in 2022. The more advanced display were required to deliver the more complicated video signals in the integrated functions such as touch. That's why we need the better, I think the better, more advanced silicon semiconductor technology will drive display. Actually, they drive each other. And Apple never wastes the spare specification, where the display size, contrast ratio, resolution, pixel per inch, we call PPI, color, touch function, etc., all improved by display technology. And the one display maker got an iPhone project if a team of Apple engineer like 20 to 30 people will stay in your panel maker's factory for 6 months, and those engineers were all the every detail in your factory. iPhone user got the certification by means of the panel actually. Apple display is as important as Apple chips. Okay, and next one, please. Next one. Yeah, I think this one we will review. Okay, back to 1984 when we start the TFT LCD manufacture. And then up to now, we can see we have a lot of breakthrough and the improvement. Okay. Semiconductor transistor was developed in 1947 at Bell Lab. And for TFT LCD was invented in 1973 at the RCA lab. Today is actually the 50 years anniversary, almost 30 years after the semiconductor. And so in the early stage, TFT LCD were processed by the machine originally designed for semiconductor, because the two kind of technology, they are different. So in the beginning stage, the yield rate for TFT LCD is very, very low. Like if we say 60% yield rate is actually was very high during that time. But 60% yield rate, we cannot make this industry successful or profitable. And so mainly the Japanese company they solve most of the fundamental issue. For example, the PI coder and the mirror projection aligner, we call MPA, and the multi-chamber sputter and the etcher were developed. And the color filter was invented and make the display become color display, and developed in the mid 1980s. In early 1990, AKT applied COMAT technology. I think this is a very, very important milestone for TFT LCD. AKT developed multi-chamber PCVD. After this, okay, all of a sudden, the yield rate become much, much higher from 80, from 60, 80 to 90, 95, okay? And also one drop fitting, we call ODF, solve the liquid crystal fitting issue for panel size over 10 inch. And the wide viewing angle liquid crystal technology, we call IPS, and the VA were developed in late 1990s and paved the way to LCTV. So we penetrate such kind of technology, make the notebook, monitor, and the TV, those three very huge major application become possible. Then TFT LCD become a big, like 150 billion US dollar business. It become the industry. And in the year of 2003, AFFS, such kind derived from IPS, but it's more advanced than IPS, were developed. The AFSS, the liquid crystal efficiency is very high, and the view angle is perfect, especially there's no coloration, means the color won't change when you change the view angle. And then iPhone apply FFS, such kind of panel in their iPhone. So then iPhone become very, very outstanding and charming. And the LCD got another big market source. So the application now extended from IT to TV, from indoor to outdoor, from car to jet fighters. So it became the all universal application technology. That's why TFT LCD becomes so successful. And next one, please. Next slide, please. Okay, now we just mentioned the AKT PCVD. As you know that the deposition mechanism in PCVD is a surface reaction, means the reactive molecule, like a silane molecule, diffuse onto the glass surface. Then on the surface, we have surface reaction to form the amorphous silicon layer by layers. Okay, and the silane molecule, if the silane molecule collide each other before onto the surface, okay, it collide on the way, it will form the cluster, means it form a lot of particle. So such kind of particle will form like a point defect, a lot of defect to that one. That's why before AKT, the yield rate is very, very low. AKT were designed the reactor chamber in PCVD. And actually it's a very, that's a, such kind of design is based on the kinetic theory of gas molecule. So that's PCVD is based on a lot of science to develop this one. Okay. And the next one, we will see another invention. Okay, there's a photolithography aligner. And in the beginning, we use proximity alignment. They actually it modified from semiconductor, but the yield rate is very high. Yield loss is very high. We form a lot of particle, so we have to use projection aligner. And but when the panel, when the panel bigger and the glass substrate bigger, of course, the length of the mirror projector aligner become very bigger and bigger too. The huge lens is very expensive, and the aligner is very bulky too. As you know that the clean room space is very, very expensive. We have to design the machine with a reasonable size to carry a lot of function. And then Nikon, they redesign such kind of optical path. The lens array replaced the giant single lens. Such kind of optical design dominate the aligner from generation 7 on and generation 8 up to generation 10. So this one so with such kind of breakthrough, we can push the substrate size become bigger and bigger from back to 1985, it's like a 300 millimeter by 300 millimeter. Now it's almost 3 meter by 3 meter. It's a kind of huge change because we have a lot of new machine and new technology to solve such kind of problem. Next one, please. The PI coater is also is a very important invention in the TFT-LCD technology. In the very beginning, we use a spin coater. A spin coater only can handle one substrate, one panel on one substrate, because the PI, the polyimide layer were spread on all over the surface. We have to use the solvent to wipe out the bonding pad portion, which is not manufacturable. which will cause a lot of damage to the panel side. And then Japanese, they invent the APR coater. The APR coater, such kind of coater, we can dispense the polyimide layer only on the panel portion, and the bonded pad portion would not coating with polyimide. And then we can have multiple panel on one substrate. We can save a lot of manufacturing costs. And it looked like a simple one, actually, but such kind of technology is not so easy, because keep in mind that the polyimide layer just only 500 angstrom by the printing technology. So the APR plate is well designed, and also the roller is very, very sophisticated too. But when the panel becomes even bigger, on the right hand side, in the left hand side, the APR coating. Oh no, sorry. Yeah, that's right. And then we use an inkjet printing method to have a better printing result. So that's another kind of minor improvement too. And next one, please. I mentioned before what ODF, one drop feeding, which solve a lot of issue. In 1980s, we use a vacuum suction chamber to do the liquid crystal feeding. Okay, we put the empty cell in a vacuum chamber, and the layers of mouse to the downward, and then we use a vacuum pump to do the suction, and once to certain kind of vacuum level, and then we put the mouse to touch the liquid crystal, and then the liquid crystal by surface tension force can climb into the cell. But the process is very, very slow. But if, for example, we have a 5-inch panel, it may take a couple hours to fill it up. I think couple hours is okay. But if we have, what if we have a 10-inch panel? It takes overnight, even 24 hours. It's not manufacturable at all. But for notebook, I think the smallest size, the minimum size is 10-inch. Even the consumer need the even bigger panel. Now people invented ODF. ODF is on the substrate, and we have a mother panel, and but the upper side and the lower side that's separated, put in the vacuum chamber. We dispense the liquid crystal drops on the panel portion by pre-calculated amount of the liquid crystal. Then the two substrates were done that, and then we cure the sealing and to sear the liquid crystal inside the panel. And that's a fundamental concept for the ODF. The concept is simple, but there's a lot of things we have to solve. The first one is the sealant. We have to use a UV curing method to cure the one, because we cannot use a thermal method, because thermal take a long time. The thermal temperature is too high, will kill the liquid crystal and the other devices. And then, so we have to solve the sealant chemical material issue. People use a lot method to formulate a new UV curing resin. Okay, the standard UV curing resin, such kind of chemical, the solvent portion will hurt the liquid crystal. So we have to use such kind of inert solvent to develop for such kind of very special resin. Another one is when we use the UV to cure the ray, but the UV, such kind of radiation will destroy the molecule of the liquid crystal. When we cure it, the liquid crystal already there. So we have to redesign the liquid crystal material. The major function group in early stage, in liquid crystal is cyanide, CM, such kind of material. Such kind of material, the bond will be broke when they receive the UV radiation. Now we replace the cyanide function group by fluoride. Now we have a fluoride liquid crystal, new kind of fluoride. Then three kinds of things put together make the ODF possible. So when we have one new technology, we need a different kind of scientist, chemical material and the mechanical engineer, and a lot of people work together. Then we have the problem. We can find a problem solution. Okay, that's what. Next one, please. Okay, now we look at what kind of TFT multi structure is. Actually, TFT LCD, they have separated technology module. Then we integrate together. Keep in mind that the TFT LCD is not the emission device. Okay, it won't. The light come from the backlight. So the light comes from the backlight, which is the first one, which is number one. And then TFT array is an active matrix which can deliver electrical signal to the piezo in a time frame without crosstalk, which is number two. And number three is a liquid crystal layer. Liquid crystal layer comprise a pair of a polarizer, a pair of alignment layers, which you will call polyimide, PI, and the piezoelectrode and the common electrode and the liquid crystal in between. The liquid crystal said the typical thickness is 4 micron. Okay, so which is number three. And number four is a color filter. Color filter create the color. Okay, and then actually the liquid crystal is a light bulb. When the light bulb on or off and controlled by the TFT array, then pass through the RGB, we can by blending we can have a multicolor. And number five is electric circuit transfer the signal into the piezo. Okay, and the last one is integrated module. For example, sensor unit. We cannot only, because TFT LCD is not the display any such kind of single function anymore. We are not only watch, but also we can play with the panel. Okay, so that's a standard aspect for TFT LCD. And the next slide, please. Okay, I think everybody's talking about the Moore's law. For example, of course, Moore's law we propose in semiconductor, and people are worried about is when now we have 4 nanometer process not already been mass production, and the 2 nano and 3 nanometer are underdeveloped. We expect to be put in mass production within 5 years, but there's a limit for semiconductor. People say that maybe 1.5 nanometer could be the physical limit. Okay, and the Moore's law, it's we also have a display Moore's law. So what is the Moore's law in display? We can see this one. In order to sustain the same panel price, the the composite performance of a display should be double in every 36 months. Why 36 months? Because the standard lifetime of one product usually is 18 months. Okay, 2 product lifetime, we have to actually such kind of product has to be obsolete, of course, become no value at all. How can we sustain the value? So by increase the serviceability or by the performance of the display. The performance of display is delivered by the panel size, 5-inch to 50-inch, where we means total different to the consumer. Resolution, contrast ratio, view angle, picture quality, uniformity, color gamma, color depth, power consumption, integrate function, for example, sensor, curvature display, form factor, and the narrow border, slimness, etc. If we can not only by the panel size, we can make the color even more beautiful. We can create another value to the panel, to the display, to sustain the price. Okay. So next one, please. Okay, in this one, we will see what kind of unit operation we have in display versus the semiconductor. There are 6 unit operation in semiconductor: thin film, CVD, thin film sputter, photolithography, etching, doping, and the thermal oxidation. We can see that the doping and the thermal oxidation, they are both very, very high temperature process, okay, over 1000. However, in display, we only have 4. Thin film, PCVD, thin film sputter, photolithography, and etching. We don't have a doping. We don't have a thermal oxidation. Why is that? Because the display is a viewing devices. Okay, we have to see this one. So we have to use a transparent substrate like a glass. Glass, I think not like silicon wafer. The glass cannot tolerate too high temperature. Okay, and especially very high temperature glass for the milk quartz, the cost is very, very high. So we have to. It's a consumer product, so we have to control the cost. So usually we control the process temperature like 250, and usually the glass can tolerate comfortably like 350. We leave 100 degree like the buffer. So in order to so as the process limit like 250 degrees, so of course we cannot use doping and some oxidation. The doping is make the contact. Okay, in thin film, in display we call thin film technology. We doping the thin film like N plus phosphor rich silicon to serve as a contact one. And also we cannot use high temperature some oxidation. We deposit like PCVD, the silicon nitride as the gate insulator to form the TFT. So that's a basic difference between the display and the semiconductor. I think that I would mention in later one that actually 200 degrees C, we find another beauty for such kind of low temperature. Let's see the next one, please. Okay, I think the semiconductor and the display, there are 2 different kind of things in the nature. And we call it the physics versus perception is the basic difference between these 2. Semiconductor require the size keep shrinking, the speed become faster, and the lower power consumption all the way. But display is different. The display is a human-machine interface. The value judged by the human eyeballs, fingers, and the enjoyment. So the screen size, response time, contrast ratio, and the viewing angle, etc. And also affordable luxury should be very important for a display requirement. Since this display is integrated by 6 independent units, like I mentioned in previous slide, display performance can be improved by 6 degrees of freedom. That's one of the reasons why since we're reaching the limit of the TFT LCD, but for example, recently, okay, people require more even more close to reality display. We use local dimming technology. Local dimming technology is we change the driving method. We change the design of our backlight. By changing this tool, we can totally change the picture quality by the backlight technology and the driving circuit technologies. Okay, the other 4 maybe remain the same. Okay, or we change the color filter material. We can have a different kind of color domain. The color domain even bigger, close to close to the movie, something like movie, not like a TV at all. So I think the human perception change by changing 1 or 2 element in display. Okay, and next one, please. For example, this one, the left-hand one is we call retina display. For a smartphone, usually retina display means 326 ppi, and for which one is iPhone 4. iPhone 3, we use a less ppi display. We can see the big difference. Okay, and now the ppi reached to 480 ppi because when your display become bigger, so we need a more sophisticated PPI, and then by different kind of method. And next one, please. So this one relate to the liquid crystal response time. Okay, we saw 2 picture on the screen. The left-hand one is a slower one, and the right-hand one is a fast one. We can see the difference. Okay, we can see the trace in the left-hand one just because the response time is too slow. So by changing if we need to change in the liquid crystal material, if the viscosity of the liquid crystal material become lower, the liquid crystal can switch in faster to achieve the high response time, faster response time. Also, we can change the electrode design. Then we can help the response time too. Also, we can use overdrive method. Overdrive means we apply the even higher gate voltage, or before falling, we drive the voltage down, and then to have a different kind of voltage applied to the liquid crystal to achieve the response time effect. Yeah, next one, please. Okay, multi-capacitor touch is a very unique user experience. I think it was insisted by Apple's Steve Jobs. I heard the story from Apple engineer. most of the Apple senior engineer saw the multi-capacitor touch cannot be possible, okay, because they find a lot of lag, but by such kind of capacitor. But Steve Jobs said that it's very cute, okay, it's cool. So Steve Jobs forced them to figure out the solution. Now they figure out, not because everybody enjoyed that one. So the zoom in and the zoom out function become the most enjoyable experience when user play with his smartphone. Okay, next one, please. So the left one is iPhone 14, and the right hand side is iPhone 6. Actually, the panel size, the difference is big, but actually the body of the phone won't change a lot, too much. Now we have to save the border. The border all occupy the panel. I mean, in iPhone 14. So we have to have the narrow border technology. As the panel become bigger, the narrow border technology make the phone size remain holding by one hand. I think that's a very basic requirement. Next one, please. I think the power saving is always very important. I think people will become very frustrated before if 2 p.m. Your phone become dead because the power consumption is too high. So people try everything possible to lower the power consumption, because if without such kind of technology, we need the very big battery, and then your phone will become very bulky. So the power saving technology is very key for smartphone. Actually, for all kind of display tech application. The oxide TFT LCD we call IGZO, Indium Gallium Zinc Oxide, with a very higher mobility, like 20 centimeter square by volt and second, compared to 1 to 3 centimeter square by volt of MOSFET silicon. And also, it's very key is that the leakage current for oxide TFT is very, very low. So such kind of thing is as long as the leakage current is very, very low, okay, we can use a low frame rate technology. The standard frame rate like 60 hertz or 120 hertz, every kind of switch we will charge and discharge the piezo, it will consume the electricity. But if we have a static picture on your screen, we don't have to switch the panel to such kind of frequency. Okay, for example, just 2 hertz. 2 hertz, we compared to 60 hertz, we can save some certain kind of electricity. Also, because the mobility is higher, so we can use a smaller TFT LCD size, can leave the space instead of occupied by the TFT, give the electrode, means that the light pass through, the light utilization rate will be higher. We combine these two advantage, we can save the power. Okay, generally speaking, we can for the switching part, we can save 10% up from that one, or from like 10%, like for example, 90 hour duration, we can extend to 100 hours. Okay, that's for LTPO. Next one, please. Okay, we can see the migration from iPhone 7 to iPhone 14 Pro Max. Okay, we see the difference from iPhone 7 to iPhone 14. The panel size increased from 4.7 inch, 5.5 inch, 5.8 inch to 6.7 inch. by narrow border technology and the power saving solution, the better size steer under well control, the form factor and the weight are managed. So we can see that actually the form function become 10 times, 20 times better than the previous one. And panel size become much bigger, but the weight is still under 200 gram or a little bit more than 200 grams, something like that. Okay, next one, please. But I think this one is very important. People say that in the very beginning, I said after 50 years, still TFT LCD not being obsolete. I think it's not a claim. We have to prove by some number. Okay, I think one of the is we study in pattern. There's a pattern life cycle, such kind of theory. We can judge if such kind of technology is reaching the saturation point or before the saturation or after the saturation become fading or not by the pattern. Then I download the top 25 US granted patent honor last year in 2022 as the table. The red one are display related. For example, Huawei, they have a lot of display pattern. Canon is a display machine maker. Okay, Apple, they have a lot of display pattern. BOE is a display maker. Samsung display, of course, is a display too. Okay. The other one, Samsung Electronic, they have all of them part of with a semiconductor. TSMC is a semiconductor. Okay. Micron semiconductor. So I think we can find that a semiconductor display automobile maker and the internet company, they are the four major players in pattern among the top 25. I would say that the display is as energetic as a semiconductor in terms of innovation. The granted pattern and the filing pattern number of TFT LCD are still increasing. The patent owner are still increasing too, because we have more and more companies still they are creating patents, and the patent number being granted by the patent office still increasing. Means we have a lot of new finding in this specific area. It means that this specific area still have a lot of room to growth. If there's a room to growth, it's not obsolete, of course. Okay, next one, please. Okay, I think people are always talking about the environmental control or to save the earth. I think carbon footprint is is a very important factor that we judge if it is a sustainable technology in the future. Okay, and the low process temperature, as I mentioned, are limited to 250 is a key index. Generally speaking, the lower temperature, the lower carbon emission, or the lower carbon footprint. LCD is a voltage-driven display, comparing to AMOLED, which is a current-driven display. In that case, voltage-driven, current-driven, they're different. So LCD is greener than AMOLED. And also, we can apply a power saving solution such as a low frame rate to LCD. There are more recycled components in LCD than other competing display technology. So I think the carbon footprint would be one of the reasons why TFT LCD will stay stay with for another 20, even 30 years. Even this technology has been on Earth for 50 years. Okay, next one, please. Next one. Okay, I think I'm going to use two figures to discuss with you about what is why we are here today, or what is the opportunity we enter this sphere. So let's take a look at the megascope figures. Okay, which is based on the GDP per capita for between Japan, Korea, and Taiwan. From late 1970s till 1990, the economy of Japan was in a very good shape, outstanding the industry technology plus wealthiness. The country is rich, companies rich, people are rich in Japan during that time. So when you have technology, you have money. So Japanese solve most of the fundamental infrastructure of TFT-LCD from when their GDP per capita over 10,000 US dollar. Okay. And then Korea and Taiwan, their GDP per capita went over 10,000 in the year like 1995, something like that. Okay. And then Korea and Taiwan both entered this TFDLC by that time when their GDP per capita over 10,000. By sharing before they have both countries, they have a good they have entered the TFDLCD for 10 to 15 years already. So they have their infrastructure has been built by semiconductor. By sharing the infrastructure built by the semiconductor, so with their 10,000 US dollar per capita, and then Taiwan and Korea start their TFT LCD journey, and actually they were very successful. Okay, so this for Taiwan, Korea, and Japan. And next one, please. Now I compare China and India, and both countries, they are big country with a big population or domestic market. China, when their GDP per capita over US $2,000 in 2005, and actually during that time, China started his aggressive display investment project from 2005. And Chinese experience proved that the GDP per $2,000 is an entrance opportunity for advanced display industry for big population country. But another thing is with government incentive, because they don't have the infrastructure. They don't have semiconductor like Taiwan, Korea. They don't have a place to borrow the infrastructure. They have to create the infrastructure by themselves. So the government should help the enterprise, the private company, to develop TFT-LCD. So I think actually from now on, now the GDP per capita for India is over 2,000 US dollar already. I think that's a right moment for India to consider aggressive to enter this very good industry. Okay, so that's the right moment. Okay, and next one, please. Okay, we come to the almost come to the end. We just summarize for period 1975 to 1990. Japan pioneered this industry. From 1990 to 2005, Korea and Taiwan joined. And during that time, their contributions were driver IC, in-house color filter, polarizer, were driven by Korea and Taiwan. And then TFT-LCD become affordable, I mean cheaper, and become bigger because become popular. Most people can purchase, like, and penetrate through the IT and TV successfully. From 2005 to 2020, China joined and become success. Japan withdrew, fading out, and the generation 8 to generation 10 become success. Generation 8.5 become the most successful, almost standard one. I think from the 2020 to 2040, another 20-year Korean will switch to MOLED. Taiwan stopped expansion. I think China cannot play, become the monopolize for this industry. We need another important figure. I think geopolitical issue and make India a very good opportunity for display second center. Next one, please. Next one. Technology-wise, okay. I just say that due to the unique integration technology structure, TFT-LCD will keep emerging. I mean, technology will keep improving. And the last, next one, please. Okay, next slide. Okay. What if we want to develop TFT industry in India? I think the most important thing, infrastructure, is the number one issue we are going to face. The upstream equipment and the raw material supplier, they are far away from, they are all in Japan, Korea, and Taiwan. It's far away from India. And so there's a cost in the beginning. Then the learning curve is another one, because the depreciation cost is around 12% for TFT-LCD. However, the OPEX is higher, is very high, 60% and even higher. So if we have a very long learning curve, I think the OPEX is a big burden to the player in India, TFT-LCD player in India. So how to shorten the learning curve is another thing. We should find that. I think it better have a capable technology partner to work together to set it up. Okay. Next one, please. This one is the last one. We just summarized them. Okay, what kind of the market size, which is 150 billion per year, panel only, approximately two-thirds of the TFT-LCD. The other one-third may be AMOLED. Okay, value chain upstream, there's another 50 billion. Downstream, okay, for TV is a 3 times higher, means one-third of the cost is panel, two-thirds will come from another component. So that's another very good business opportunity. Monitor is 1.5 times, notebook is 8 times higher. Smartphone is even higher, 10 times, 20 times. And the car is 100 times, means $1 display, we can make $100 car, something like that. The driving force, okay, with this one, we can drive not only the panel itself, it will drive fine chemical, precision mechanical, AI, and the service system, semiconductor industry, because semiconductor will get a benefit for that one. And another one is talent pool. We have provide very good job opportunity for Indian talent. I think that's all for my presentation. Thank you very much thank you for your attention.
Thank you, sir. Now we'll take the question from audience. So the first question is asked by Rajan Singh. Kindly elaborate more about color filters in TFT LCD. What are these materials?
What kind of, what's your question again? Hello. I think liquid crystal is a kind of organic material. Okay, it's basically like it's a kind of organic. Means the organic there's a carbon but the key is we have to carefully design the liquid crystal. It comprises the first one is twist material. It's like the Cairo. It's a twist. Twist 90 degrees, something like that. We have to control by the Cairo material. Another one is the optical material. It will control the birefringence, such kind of material. Then we can have the live material coupling with the polarizer, such kind of materials. Yeah.
The next question is quantum dot based displays better than LCD?
I think the quantum dot is not is assistance to TFT LCD. Quantum dot means when light goes through the quantum dot, we can trigger on another quantum effect, where enhance the light usage. But basically, the light bulb still controlled by TFT LCD. I think these two things put together will become the more powerful TFT LCD. So quantum dot itself is not a display, just is a very important kit or component for TFT LCD.
But the next question is, which material or technology is preferred for the display back panel?
What kind of material display back panel?
amorphous.
OTFT or amorphous?
I think because amorphous TFT LCD is still the most popular use section for TFT LCD, because amorphous silicon is most cost efficient. It's a very cheap. Yeah, very cheap compared to polysilicon. Polysilicon, I mean, the capital investment per is about 3 to 4 times higher than that one. I mean, the capital cost is much higher, and the process is even longer. In TFT LCD, we only need the 4 mask or 5 mask in the array portion. For polysilicon, we need 7 to 9 masks. I mean, the cost is much higher. But the polysilicon will work for like very high-end smartphone. We need a very high PPI. So if the PPI higher than 350, we have to use a polysilicon. I think people will pay for that. But for commodity product like a monitor or notebook, there's no reason use polysilicon. It's no meaning. We have to use TV. We use amorphous silicon. I think more than 90% of the production area we use amorphous silicon. Yeah. But the voice broken.
Can you hear us, sir?
Right now, yeah, it's kind of broken, right? Yeah, on or off. Can you hear me?
Yes.
Yeah.
Sir, I was asking which one is preferred by Vedanta? Which material is preferred?
But yeah, I'm right now a consultant to Vedanta in develop this project because I think we can in Taiwan we can find the best technology partner. I think the partner will cooperate with Vedanta from end to end and hand on hand to work on this one. I think that's it's a very important success factor for India, for Vedanta, because we can provide a very good technology source from Taiwan, and Taiwan this company, they have a very strong willing to work together with Vedanta for the next 3 to even 5 years. I think it takes time because not only the manufacturer, product design and the year improve, and the marketing development, there's another know-how to share with. Yeah.
Thank you, sir.
Okay. Thank you very much.
Thank you.
Now it's time for lunch break. I request all the participants to kindly join again by 1:45 p.m. for the upcoming talks. Thank you.
Thank you. Bye-bye.
Certainly this thing.
What is it?
That INUP thing, they were teaching us simulating things from Silvaco. The system is slow, can't do much.
In our this one, no seminar hall we have this one. What is it called? Wi-Fi.
Wi-Fi means.
Wi-Fi is there in our seminar room.
Yeah, yeah. Why sir? Oh, for that there. Yeah. Making different concentration of the starch triodize again to see if it works.
You got some figures or not?
No, so that's why I'm increasing the concentration and checking.